The normal distribution curve is kind of like this. I can never draw it straight. That's a normal distribution curve. The total area under the curve, it's like the total probability. That's 100%, or we usually say 1. When you say the standard normal curve, that means that you've got your z-scores on your x-axis. So your z-scores will be 0, 1, 2, 3. And negative 1, 2, 3. So the standard normal distribution has a mean of 0 and a standard deviation of 1. Other things to notice, look at the z-scores. The z-scores can be positive or negative. A positive z-score means that your data value is above the mean. A negative z-score means that your data value is below the mean. But the probabilities, the area under the curve, those are all positive numbers between 0 and 1. Probability distribution. First of all, what is a probability distribution? A probability distribution has data values and then probabilities that go with each data value. So like maybe this is ages of kids in a preschool. So if your age was 1, what's the probability that you were in that preschool? 0.1. If you're an age of 2, the probability was 1.1. Wait a second, that doesn't make sense. A probability of 1.1? You can't have over 100% of the people, so that is not valid. Your probabilities down here have to be between 0 and 1, which also makes this one not valid because this is a probability. You can't have a probability of negative 0.1. So again, these are your data values, and this is the probability that you have that specific data value. The other thing about a probability distribution is that all your probabilities have to add up to be 1. So when you add all these, you have to get 1 for it to be a valid probability distribution. Because all the things that could happen should add up to 100% of the time. In this case, it isn't. If you add those together, you get 1 and 1/6. So that's not a valid probability distribution. But if you add up these probabilities, you can see that they sum to 1. So that is a valid probability distribution. D. 3. What value would be needed to complete this probability distribution? So again, we know that all of these have to add up to be 1. Again, these are our data values, 0, 1, 2, 3, 4. Maybe this is the number of kids you have or something. So about 33% have 0, about 12% have 1, 25% have 3, 16, 17% have 4. This would maybe say 4 or more if that was actually the number of kids. But we need to find this number. Well, we know they add to 1. So you just take 1 minus the rest of these things, and you'll get your answer, 0.125. These are just formulas. We're finding the z-score. So you go to your formula sheet, and you might find this on your standard normal curve probability table formula sheet as well. But it says find the z-score. So you find the formula that says z equals, and then it's x minus mu over standard deviation. X is our data value, mu is our mean, sigma is our standard deviation. So our data value was 53, that's the score there, minus our mean was 72, and standard deviation was 10. Negative 1.9. That's kind of what I expected too, because I know the data value 53 is below the mean of 72. Therefore, I know I'm going to get a negative z-score. Negative z-scores go with data values that are below the mean. This time I already have the z-score. I want to find out the x. What was the data value that goes with that z-score? So I use the other formula. In words, this says the data value is the z-score times the standard deviation plus the mean. So the z-score I want is 1.96 times the standard deviation, which is 35, plus the mean, which is 450. So this is the raw score. And again, make that make sense. If the mean's 450, your z-score is 1.96. That means your 1.96 standard deviation is above the mean, so you should be above the mean. And I am above the mean. At this point, I want to talk about your formula sheet a little bit, especially the stuff in Chapter 5, as we haven't done it for a while. Chapter 5 has probability distributions and binomials in it. So I like to do this. This is the stuff for probability distributions. So if you have the table that shows every possible value that you can get, and then every possible probability, and they add up to 100%, that's a probability distribution. So if you're asked for the mean of a probability distribution, it's right here. If you're asked for the standard deviation of a probability distribution, it's right here. If you're asked for expected value or expectation, it's right here. What about if you have a binomial? Binomials are right here. You probably have, instead of this piece right here, NCX times P to the X times Q to the N minus X. So if you have a binomial and you want the mean, the formula is right here. Standard deviation, right here. First off, what is this table called? This is called a probability distribution. It shows all of the data values you can get, and then the probability of each data value happening. These probabilities will always add to 1 or 100%. To find the mean, I go to my formula sheet and I look up the mean of a probability distribution. It'll tell me that the mean is the sum of the XPX column. I look up the standard deviation of a probability distribution, and it will tell me this: square root of the sum of x squared px minus the mu squared. So then I go back up. I need the xpx column and the x squared px column. So to get xpx, I just take the x value times that probability, and so on. To get the x squared px, I take the x value, in this case 8, and square it. 8 squared times 0.2. I filled out the rest of the table. Double check your x squared times px column. Some people get that wrong. I've also summed each of those columns because I'll need them to find my mean and standard deviation. Here are the formulas for my formula sheet. To find the mean, all you have to do is sum the xpx column. Here's the xpx column. We've already summed it, so our mean is 11.4. Standard deviation. I'm just going to follow this formula. I want the square root of the sum of the x squared px column. Here's the x squared px column. We already figured its sum. Minus the mean squared. Well, here's the mean. 11.4 squared. So I plug this into my calculator. I get 2.37 or 2.4. I'm looking for the expectation of the game. So I go to chapter 5 on my formula sheet and I look up expectation. Expectation, E of x, is the sum of the xpx column of a probability distribution. So I know I've got to make a probability distribution. I don't have a lot of room. I'm going to try to do it over here. I'm going to have an x column, a p of x column, and then an xpx column. The x is kind of like saying your net gain. So over here I'm going to make a little label here on the side. The first thing that could happen is I could get a sum of 9. So on the side I'm going to write a sum of 9. And then what is my net gain there? Well, if I have a sum of 9, I win $10, but it cost me $5 to play the game. So my net gain is $5. I won 10 but had to pay 5, so my net gain is 5. I could also get a sum of 3. How much would I have for x there, net gain? Well, I'd win 20, but again, I have to subtract 5 off because it cost me 5 to play the game, so I'd actually win $15. Or what's the other thing that could happen there? I could lose the game. Anything else loses the game. What's the net gain there? -5. You lost $5. Now I need to know the probability of each of these things happening. I go to my formula sheet, find the sample space for rolling 2 die. I see that there's 36 things that could happen. How often out of those 36 choices do I get a sum of 9? Well, 3 and 6, 4 and 5, 5 and 4, 6 and 3. 4 choices. So there are 4 choices out of a total of 36, 436, that I will get the $5. A sum of 3. There's only 2 ways that can happen. 1 and a 2, 2 and a 1. Again, I'm just looking at the sample space on my formula sheet. So 2 out of 36 that will happen. You can reduce these if you want to. So what's the probability I'll lose? Well, 4, 5, 6 times out of 36 I'm going to win. So that means 30 times out of 36 I'm going to lose. Now I fill out the x times px column. So on my calculator I do 5 times 4/36. It tells me 5/9. 15 times 2/36. And -5 times 30/36. Then I add these up, sum these, and I get -2.78. That's the sum of the xpx column. That is the expected value. That means on average, if you averaged everybody together, all the winners and all the losers, you'd average that people lost $2.78. Binomial distribution. First, what makes this a binomial? It's because there's only 2 choices. Your box contains white balls and black balls. You're either white ball or black ball. Some other examples would be a test. You either get a question right or you get it wrong. A fishing trip. You either catch a fish or you don't catch a fish. There's only 2 choices. That's binomial. What is the probability that the person draws a white ball exactly 3 times? The experiment is done 10 times. 3 white balls, 2 black balls. To do binomial, you need to know n, x, p, and q. N is the number of times that you do the experiment, 10. X is the number of successes that you're looking for, exactly 3 times, so N is 3. Probability of success, in our case, draw a white ball exactly 3 times. So what's the probability that they're going to draw a white ball? Well, look at your box. Your box has 5 balls altogether. 3 of them are white, so the probability of getting a white ball is 3 out of 5, 3/5. I like to use the decimal, 0.6. So what's Q? Q is the probability that you don't draw a white ball. So 0.6 is the probability you do. You do 1 minus 0.6 to get 0.4. 60% chance you will draw a white ball, 40% chance you won't. Another way of looking at that is the chances is 2/5 that you'll get something other than a white ball. The question asks you to use table B. So you go to table B, the binomial table, which will be included on your test. Look up N is 10, X is 3, P is 0.6, and look for the probability. You could also have used the formula for this problem. That would have been this. Number 10, what is the probability of drawing at least 7 white balls? At least means, at least 7 means that it could be 7 or 8 or 9 or 10. So again, you're doing the experiment 10 times. Your X that you have to look up is all those, 7 or 8 or 9 or 10. P, again, probability of a white ball, 0.6. Q, the probability of not a white ball, 0.4. So you go to your table and you look up N is 10, P is 0.6, X is 7, that probability is 0.215. When N is 8, I'm sorry, when X is 8. When X is 9, when X is 10. Add those together, 0.382 is the probability of drawing at least 7 white balls. What is the mean of the number of white balls drawn? I go to my formula sheet. I find the section for binomial in chapter 5, and I look up the formula for the mean. It tells me that it's N times P. In my case, N was 10, P was 0.6. This time we're supposed to use the formula. So you go to your formula sheet and write down your formula. Then let's figure out each of our pieces. N equals 8. X, how many successes are we looking for? Exactly 4, so N is 4. P, 0.32, the probability of success. So Q is the probability of not success, so you do 1 minus 0.32, you get 0.68, and you plug all those things into your formula. Times P to the X, so 0.32 to the 4th power, times Q to the N minus X, so 0.68, N minus X 8 minus 4 is 4. Plug that into your calculator and find the probability. Area under the curve between a z-score of negative 1.89 and a z-score of 0 be this area. You look up these two z-scores and find their probabilities. And subtract them. A. Using the standard normal, what is the probability that z is greater than negative 1.64? Negative 1.64 is about here. We're looking for greater than. We'll look up a z-score of negative 1.64 in our table. We get that the area to the left is 0.0505. So we know that this area right here is 0.0505. Our table always tells us to the left. So to find that area to the right, the greater than, we do 1 minus. D. Using standard normal, the statement says, what is the probability that the z-scores are greater than 2.09? 2.09 is about here, so I want to know this probability. I go to my chart, I look up 2.09, and I'll find the area to the left of. So that area to the left of, right here, 9817. I know the whole area is 1, so I take 1 minus 0.9817. And that'll give me the area to the left, the probability to the left, B. 16. Using the standard normal distribution, what is, okay, let's translate this first. The probability that the z-scores are between 1.8 and 2.39. So this area. So I'll look up the probability. These are the z-scores. Z-score of 1.8, z-score of 2.39. I look those up on the table, and I find the probabilities that are to the left of each of those. So for the z-score of 1.8, the probability that you're to the left of it is 0.9641. And for the z-score of 2.39, the probability that you're to the left of it on the table is 0.9916. I subtract the two to find the area in the middle. A. 17. What is the z-value to the right of the mean where 59.18% of the distribution lies to the left of it? So I have the percent, 59-ish percent. I'll change that to a decimal, 0.5918. And then I want to shade. Let's see, I know that half of it is 50%, 0.5, so it's probably going to be a little more. I'm guessing that my z-score is going to be right about there. And that will mean that this is 0.5918. So this is my probability. And then I'm looking for the z-score that goes with that. So I go to my table and I look in the middle. Look in the middle numbers and try to find 0.5918, or as close as you can get to it. Then look at the z-scores on the outside and find the z-score that matches up with that. When you do that, you get a z-score of 0.23. A large department store, the average number of years of service, so the mean amount of service was 13.5 years, with a standard deviation of 6.2. If an employee, so one employee is picked at random, what is the probability that the employee had worked between 8 and 20 years? So what's the probability that our data value is between 8 and 20? Okay. Well, I've got two data values there, an 8 and a 20. So those are my x values. So I'm going to start out with x is 8. I need to turn that into a z-score. I do that by using my z-score formula. The z-score is the data value minus the mean over the standard deviation. So that'll be 8 minus 13.5 over 6.2. So I'll simplify that and I'll find that the z-score that goes with 0.8 is negative 0.89. Then I go to my table. I put the z-score on the side of the table and I find the probability that I'm to the left of that z-score. I read off the probability from the inside of the table, which is 0.1867. Now I'll do the same thing for the data value of 20. Again, I'm going to use this formula to change my data value into a z-score. Z-score is the data value minus the mean divided by the standard deviation. So I find that the z-score, I plug that into my calculator, I get the z-score is 1.05. That's the z. So what's the probability that I'm to the left of it? I go to my table, look up on the sides, 1.05 for the z-score, and find the probability in the middle of the table. So what's going on over on my picture here? I've got a data value of 8 that corresponded with a z-score of negative 0.89, and I've got a data value of 20 that corresponded to a z-score of 1.05. And I'm looking for the probability that I'm in between. So I take this probability and minus this probability. And it gets C. Again, average years of service was 13.5. Standard deviation, 6.2. If an employee, one employee is picked at random, what's the probability that that company has worked, that employee has worked for the company less than 14 years? So the probability that the data value is less than 14. Well, that 14, that's my x, that's my data value. So I have to figure out the z-score that goes with that. Again, the z-score formula, data value minus mean over standard deviation. So my data value is 14 minus the mean minus 13.5 over 6.2. So my z-score associated with the data value of 14 is 0.08. I go to my table and I look that up. The probability that we're to the left of 0.08 is 0.5319. And that's it. My z-score of 0.08, that's right here. The probability that I'm to the left of that is 0.5319. If it said to the right, I would do 1 minus this. But since it's to the left, my table gives it to me exactly. Okay, the average score on this entrance exam is 142. And standard deviation is 16. I want the top 15%. Well, if the average is 142, that's right here. I want the top 16%. I don't know, maybe right here. I'm kind of guessing. So that would be 0.1600. No, sorry, 15% I want. 1500, 15%. So then this area, the area to the left, which is what my table shows, is going to be 0.8500. So I want to know, what is this z-score? What is that z-score that has 85% of the data to the left of it? So you go to your table, you look at the middle where the probabilities are, and find the number as close as you can get to 0.8500. Then you look on the outside. That sometimes takes me a while. Then you look on the outside. What z-score did that go with? Turns out that z-score it went with was 1.04. Now that you have the z-score, 1.04, now you have to figure out what data value that went with. So you use that formula, find the data value given the z-score. You take the z-score times the standard deviation plus the mean. So then you plug that in. The z-score is 1.04 times the standard deviation, 16, plus the mean, 142. Plug that into your calculator. You get 158.64. So that's going to be B, 159 or above. A study showed that an average number of hours that children in the U.S. watch is 4, so the mean is 4, and the standard deviation is 1.6. If a group of 64 children is selected at random, what is the probability that the average time or the mean time that the children watch TV is more than 4.3 hours a day? So what's the probability that the mean time that that group watches is greater than 4.3? The 64 people, that's the group, that's the sample of students that I'm taking. So that means that my N is 64. Now what this stuff tells me right here, that I have a group of 64 people that I'm doing the mean time that the kids watch, is that instead of using my z-score formula that I used up above, I'm going to use this z-score formula. So I've got this mean value. Instead of having a data value of 4.3, instead of talking about one kid watching 4.3 hours a day, I'm talking about the mean of a sample. And that mean of my sample is 4.3. What's the probability that it's going to be over that? So I need to find the z-score that goes along with that. So I'm going to use this formula right here. X bar, that's the mean that I have, 4.3, minus the population mean, 4, divided by the standard deviation, that's 1.6, divided by the square root of n, the number of people in our sample, 64. That z-score ends up to be 1.5. Okay, that's the z-score I'm looking at. So now I work it just like I worked problems 18 and 20, 18 and 19. I go to my table. I'm going to make this picture. I want that it's greater than that. So I want this number. I go to my table. I look up on the sides a z-score of 1.50, and I find that the probability that I'm to the left of that z-score is 0.9332. So this area is 0.9332. I want to the right, so I do 1 minus that. And I get B, 0.0668. Number 22. First, is this binomial? Well, so getting points on a final, you're either going to get the point or you're not. So it's either right or it's wrong, basically. So that is a success or failure, so that's binomial. The other thing that would have to happen to make this a binomial is we would have to assume that she has the same chance of getting problems right on a quiz as she does on her test, and we'll just assume that. I like to use the binomial distribution table and procedure table on page 340 for this. So I'm going to follow the steps that are there. First off, things we need to know. We need to know n. What's the total number of points or total number of trials? 200. There's 200 points on her final. And then what's p? What's the probability of success on a point? Well, we're going to assume that it is 0.82, 82%. So then what will q be? The probability of failure on a point? Well, 1 minus 0.82, which is 0.18. So 82% chance you're going to get the point, 18% chance you're not going to get the point. Okay? So, step 1. The first thing we have to do is check, is it even possible to use standard normal curve when approximating a binomial? And basically what you're looking for is if your trial size is big enough. But here's what step 1 says to do. Take the number of trials, n, ours is 200, and times it by, multiply it by p. You get 164. You want that number to be greater than 5, which it is, so we're good there. Next, you have to check q. Take n, again 200, times q. You get 36. So both of these numbers, 164 and 36, we have to check that they're greater than or equal to 5, and they are. So step 1 is a success. We are allowed to use the standard normal curve for approximating this binomial. Step 2. You have to find the mean and standard deviation. Where do you find that? There's formulas for that on your green formula sheet under Chapter 5, binomial, mean, and standard deviation. You'll see that the formula for the mean is n times p. We already did that. 200 times 0.82 is 164. So that's our mu. And then we need standard deviation. I look in Chapter 5's formula sheet and I find that the formula for that is the square root of n times p times q. So I'll find that. N is 200 times p, which is 0.82, times q, which is 0.18. I throw all that into my calculator, and I have my calculator figure for me, and it's 5.43. That's my standard deviation. Next, step 3. Write the problem using X notation. So step 3, that's right here. This one's a little tricky. It says she will get at least 160. What does at least mean? At least 160 means that she gets 160 or more. So how do I write that? Well, it's right here. The probability that the score is greater than or equal to 160. Now we have to do step 4, which is to adjust it. And so we go to our table on page 340 or maybe on your formula sheet, and we say, okay, if you have x is greater than or equal to a, then that changes to x is greater than, it tells me to do a minus 0.5. So I'll do minus 160 minus 0.5, I get 159.5. then that's the number that I change into the z-score. So step 5 is to then change that data value into a z-score. I do that by using my z-score formula. Data value minus mean over standard deviation. So I'm going to use the 159.5 for my data value, my adjusted number, minus the mu. You find the mu back in step 2. We figured out what the mu was. And the standard deviation, also in step 2, we figured out what our standard deviation was. So that is my z-score. So now I have to draw my picture and think about what probability I'm looking for. So z-score of negative 0.83, that's about here. And what did I want? I wanted that the probability of that z-score being greater than. I wanted to get 160 points or more, so it's more than that. So this is the number that I'm looking for right here. So then I go to my z-score table, and I look up the z-score for negative 0.83, and I find that the probability that we're to the left of that from my table is 0.2033. So the probability of being to the left of that z-score is about 20%. But I don't want the left, I want to the right. So I'm going to do 1 minus. It's about a 79–80% chance that she's going to get at least 160 points out of 200 on her final.